Hello, this will be a demonstration of Proposition 2 from Book 7 of Euclid's Elements, which requires us to find the greatest common measure of two numbers which are not prime to one another. What we're, of course, given is two numbers, AB and CD, and these numbers are not prime to each other. Of course, if they're prime to each other, then their greatest common measure is the unit. That's just obvious. So we're given two numbers that are not prime to each other, and the task at hand before us is to find their greatest common measure. Now, it is either the case that the number CD measures the number AB, or it does not. If it does not, then the number CD is manifestly the greatest common measure of the numbers AB and CD, so the number CD measures AB. The number CD also obviously measures itself, so it is a common measure, and furthermore it's the greatest because there is no number greater than CD which can measure CD. And so if the number CD measures the number AB, it is manifestly the greatest common measure of the two given numbers, AB and CD. But this is, of course, not the only case. It might be that the number CD does not measure the number AB. In fact, that's much more likely given two non-coprime numbers. Now, if this is not the case, then if we go through this process of continual subtraction like the previous proposition, we go through this antenaresis is the word, we will not be left with a unit, but instead we will be left with some number that measures the one before it. If we are left with a unit, then the numbers AB and CD will be co-prime to each other by proposition 7.1, but this is contrary to the hypothesis. It is contrary to what is given. For we were given that the numbers AB and CD are not co-prime to each other. So if we go through this process of antenaresis, this continuous subtraction, we won't be left with a unit, and thus the only other number that we will be left with is one that measures the one before it. So let's go through this. We'll take the number CD and we'll measure it through AB up to the number BE with the remainder EA. Next, we shall take the number EA and measure it through CD up to the number DF, leaving as a remainder the number FC. And this number FC will be such that it measures the number EA. Again, because the numbers A, B, and C, D are not co-prime to each other, we will end up with a number that will measure the one before it. And we're just going to stop it here and say that the number CF measures the number EA, which came before it. Now, because the number CF measures the number AE, we came upon the number CF such that it does measure the number AE. Furthermore, that the number AE measures the number DF, right? We made DF such that it is measured by AE. It is obviously the case by a property of numbers that the number CF will also measure the number DF, which means that the number CF measures both DF and FC, right? It obviously measures itself, and so it's going to measure their sum. This is, again, a property of numbers, so if we take the example that 3 measures 6 and it measures 9, which means it measures 6 plus 9, which is 15, and 3 obviously does measure 15. So we know that the number CF will measure the sum, which is the number CD. But we know that the number CD also measures the number BE, right? We established BE such that it is measured by a CD in the third step. So it's obviously the case that the number CF will also measure the number BE by a property of numbers. Now we know that the number CF also measures the number AE, right? We established that in the third step, which means that it measures both the numbers EA and BE, which means that, again, it will measure their sum, which is the number BA. So the number CF will measure the number BA, but it was also shown that it measures the number CD, which means that the number CF is a common measure of the two numbers AB and CD. Now, I say that it is also the greatest common measure in that there is no other number which measures both AB and CD which is greater than CF. For if this is not the case, then there will be such a number, we'll call it G, such that the number G is a common measure of AB and CD, and that it is also greater than the number CF. Now, the number g measuring the number cd, we created g such that it does that. And the number cd measuring the number be, again by step 3, the number g will also measure the number be. But it was also said that the number g, it measures the number ab, which means that it'll measure the difference of ab and be, again by a property of numbers, so that the number g will measure the number ae. But we know that the number ae measures the number df. We made df that way in the third step, so that the number g also measures the number df. But again, we made the number g such that it measures cd, which means that it will also measure the difference between cd and df, so that the number g measures the number cf. Now, if a first number measures a second number, then that first number will obviously be less than the second number. 3 measures 9, so that 3 is less than 9. So we can say that the number g is less than the number cf, which means that the number g is simultaneously greater than cf. We made it that way in step 8. But it has also been shown to be less than the number cf. We've just proven that in the 12th step, which means that the number g is simultaneously greater than and not greater than the number cf. This is manifestly absurd. And so we can say that the number g is not the greatest common measure of the two given numbers a, b, and cd. And we can prove this with any other number that exceeds cf, so that we can say in the end that the number cf is the greatest common measure of the numbers a, b, and cd. And this is precisely what we set to find, so that we are done with the proposition, therefore, etc., q, e, d. I actually forgot to write that. Okay, q, e, d. There is a Poorism appended to this proposition that states that if a number measures two numbers, that number will also measure its greatest common measure. So, for example, if we take, what's an example? 12 and 18, their greatest common measure is 6. But we can also say that the number 3 is the common measure of 12 and 18, which means that it'll measure their greatest common measure, that is 6. 3 obviously measures 6, so this Poorism checks out. Now, like the previous proposition, this one is a little tough to understand without an example, so let's go through one. We'll take the two numbers 84 and 108. We'll have 84 and 108. Now, these are obviously not co-prime to each other because they're both even, which means they're both divisible by 2. So we have two non-co-prime numbers. Let's find their greatest common measure. We begin by doing this process of continuous subtraction. We'll go through anti-analysis again. So we'll do 108 minus 84. That will leave us with 24, like that. 24 is less than 84, so we'll go through the process another time. We'll do 84 minus 24. This will leave us with 60. We can subtract 24 from this again. 60 is greater than 24. So we can say that 60 minus 24, that is 36. Again, 36 is greater than 24, so we can subtract it again and say that 36 minus 24 is 12. Now, we have hit the number 12, which measures the number before it, that is 24, right? 12 measures 24. And so, yeah, we confirmed this second step up here, that if you do anti-analysis with two non-co-prime numbers, then we'll end up at a number that measures the one before it. In this case, where we have 84 and 108, we arrived at that with 12 and the number before it, 24. And having arrived at this number 12, which measures the number before it, that is 24, we can safely say that this number 12 is provably the greatest common measure between 84 and 108. And this is obviously the case. So this process of anti-analysis checks out as a reliable way to find the greatest common measure of two non-co-prime numbers. One final note, it's obviously the case that that the greatest common measure, what we now call this, is the greatest common denominator. So that the number 12 here is not only the greatest common measure of 84 and 108, it is also their greatest common denominator. So yeah, that's just a translation barrier between Euclid's math and the language that he uses, and how we now talk about number theory and greatest common denominators. That being all I have to say about this proposition, I will end the video here and move on to proposition 7.3.